Good evening everyone. My name is Renu Raman Sahu and today we will be discussing some of the assignment questions of week 10 and some of the previous year questions. So let us go to the first question. The value of critical temperature is dash Kelvin if the critical magnetic fields of a superconductor at temperatures 4 Kelvin and 8 Kelvin are 11 milliampere per meter and 5.5 milliampere per meter. So this is a formula based question, and the formula of the critical fields and the critical temperature, it has to be known as a function of temperature, and the relevant formula is this. So the critical temperature Hc, the critical field at temperature T is given by the critical field at temperature 0 Kelvin, and we have to multiply that with 1 minus T over the critical temperature and the square of that. So this is your formula that you have to apply. So here you see we don't know what is this H naught, but we know this Hc at two different temperatures. Let's say that Hc1, so this is for the 4 Kelvin. At 4 Kelvin, T1 equal to 4 Kelvin. Hc1 is equal to H naught 1 minus T1 by Tc whole square, and at T2 is equal to 8 Kelvin. We have H2 is equal to, or like critical field, Hc2 is equal to 5.5 milliampere per meter. 5.5, here Hc1 is 11, so here Hc2 is equal to H naught 1 minus T2 over Tc whole square. Then what we have to do, so we know Hc1, T1, Hc2, T2, so we just have to divide both of this. So from here what we can obtain is Hc1 by Hc2 is equal to 1 minus T1 by Tc whole square over 1 minus T2 by Tc whole square. So now what you have to do is you just have to put the values and you have to just rearrange. So let us just do that. So from here Hc1 over Hc2 1 minus T2 by Tc square is equal to 1 minus T1 by Tc square. So we just need to rearrange now. So it is Hc1 over Hc2 minus Hc1 over Hc2 T2 by Tc whole square equal to 1 minus T1 by Tc whole square. This implies T1 by Tc whole square minus Hc1 over Hc2 T2 by Tc whole square is equal to 1 minus Hc1 over Hc2. Now we want Tc square to be there, so we'll just separate the variable. So T1 square minus Hc1 over Hc2 T2 by, okay, so it is T2 square, and this is equal to, so divided by 1 minus Hc1 over Hc2 is equal to Tc square. So this implies, now we just have to put the values and get the answer. So T1 is equal to, T1 and T2 are 4 and 8, 4 square, so this is Tc square, 4 square minus 8 square and Hc1 and Hc2 are 11 and 5.5, so it is 11 by 5.5, 1 minus 11 by 5.5, so Tc square is equal to, so this you can simplify, 4 square minus 2 into 8 square, 1 minus 2, so it is just minus 1, so it is 2 into 8 square minus 4 square. So this implies Tc is equal to 2 to 2 square 4 square minus 4 square by 2, which is nothing but 4 into root 7 Kelvin. So this is your correct answer, 4 into root 7 Kelvin, and if you calculate 4 into root 7, it will turn out to be around 10.58 Kelvin. So your critical temperature is around this value. Now let us go to the next question. Considering the Bezier theory of superconductors, which of the following statements is not correct? So let us see, the presence of energy gap at temperature below the critical temperature. So this statement is correct. So why? Because at temperature T less than the critical temperature, there would be a energy gap between the superconducting electrons. So let's say that this is the superconducting electrons, and there would be the normal electrons, which this is the energy level of the normal electrons. So that gap is there, that gap is there below the temperature T equal to Tc, okay, below the critical temperature. So the presence of this gap is there, so it is true. At different critical temperature for isotopes. So if you have two different isotopes, let's say M1 and M2, then the critical temperature changes, and it is observed that the critical temperature Tc is inversely proportional to the square root of square root of the critical mass. So so therefore it is true that different isotopes will have different critical temperature. So this statement is also true. RUA, this we discussed to be true. The quantization of magnetic flux in superconduction ring in the unit of H by E. So this statement is not correct. So the quantization of magnetic flux, it happens always at H over 2E. Quantization of magnetic flux in superconduction ring in the unit of H over 2A. So the factor of 2 is missing here, so that is why this is not correct. So the presence of Meissonier effect, this is true, like a widely known effect, that if so there would be no magnetic field lines inside the superconductor below the critical temperature. So this is also true. So your correct answer is this one. Let us go to the next question now. Which of the following is true for magnons in a ferromagnet? So magnons are what? Magnons are the spin waves, or the quantum of the spin fluctuations. So for example, if you have a spin arranged in a lattice like this, so this would make, let's say this is making some angle with the spin, this is making some angle, this is making some angle. So this phenomena, so this kind of wave, this is called, so the quantization of this wave is called a spin wave or a magnon. Okay, so you can like trace out. It turns out that so these magnons are bosons actually, and since they are bosons, they satisfy Bose-Einstein statistics. So the first statement that magnons are fermions and hence follow Fermi-Dirac statistics, this is false. At long wavelengths, the frequency is proportional to k square. So if you calculate the dispersion relation, it turns out to be h cross omega. So JS, 1 minus cos Ka. So at long wavelength, what it means? Long wavelength means say K equal to 2 pi by lambda. Yeah. So at long wavelength, what do we mean by long wavelength? Long wavelength limit means lambda goes to infinity. So k goes to 0 because k is 2 pi over lambda. So at small k, this k times a is also small. So k a is small. So what we can do is we can expand this cos ka around ka equal to 0. So if we do that, so it is js1 minus ka whole square by 2 factorial plus ka to the power 4 by 4 factorial minus so on. This would be the expansion of cos ka. Now we keep terms up to the, so this is okay. So this is 1 minus cos ka. So this expression corresponds to cos ka, the expansion of cos ka, and this is what we have, h bar omega. Now what we are going to do, this 1 will cancel this 1 and we keep terms up to the order ka to the power 4 square. Okay, we keep terms up to this order and neglect the higher order terms because ka is really small. So since it is small, we can neglect higher order terms. Its square will become furthermore small. So h bar omega is js k a k square a square by 2. So what we see from here is that omega is directly proportional to k square. So this statement is correct, or this is true. Since we proved that at long wavelengths the frequency is proportional to k square, so this is not true. Just now we saw, and none of the above is true. Like this is also false. So the correct answer is this one. Now let us go to the next question. The thermal conductivity of a given material reduces when it undergoes transition from its normal state to its superconducting state. Okay, the Cooper pairs cannot transfer energy to the lattice. This statement is false. The Cooper pair can still transfer energy to the lattice. Upon the formation of Cooper pairs, the lattice becomes less efficient in heat transfer. So this statement is also not true. The electrons in the normal state lose their ability to transfer heat because of their coupling to the Cooper pairs. So this is again not true. The electrons will not lose their ability to transfer heat. So the correct answer is that there is a gap opening on the transition to the superconducting state, so that the minimum energy required for the excitation of each electron from a state below the gap to a state above the gap, leading to a reduction in thermal conductivity. So what happens is, if you have if you just plot thermal conductivity, for thermal conductivity you need certain amount of electrons. Okay, so thermal conductivity requires now in a superconducting state, what will happen? So there is this superconducting state and superconducting state, and there is normal state, and there is this gap. There is this gap which has opened up. Now if you want so some of the electrons which are in superconducting state, for them you need to give certain extra energy so that they come to the normal state and can conduct the heat and can conduct the or participate in the heat conduction. So that is why the thermal conductivity, so because of the presence of this gap, the thermal conductivity will reduce. So this is your correct answer. Let us go to the next question now. The critical temperature of a material with isotopic mass is 199 atomic mass unit, is 4.185 Kelvin. The critical temperature if its mass changes to 203.4 atomic mass unit is dash Kelvin. So the way you solve this question is you need to know the fact that the critical temperature Tc is inversely proportional to the square root of the isotopic mass. So you are given two temperatures at T1 is equal to 4.185 Kelvin. Your isotopic mass M1, let's say, is 199.5 atomic mass unit. So you've been asked a temperature at what Kelvin your isotopic mass will become 203.4 atomic mass unit. So what you have to do, you just have to use this relationship. Tc is equal to, let's say, some proportionality constant K over root M, where K is some proportionality constant. So if you divide the expression of T1 by T2 is equal to M1 by M2 square root, and you need to find what is T2. So T2 is equal to T1 into M1 by M2 square root. So T1 is how much? 4.185, and square root of M1 is 199.5 divided by 203.4. So if you calculate this, you will get so it is 4.185 into square root of 199.5 divided by 203.4. 4 point. So you will get 4.145 Kelvin, near to this. Now let us go to the next question. Which of the following statements is or are correct about the type 1 and type 2 superconductors? So superconductivity is abruptly destroyed when the strength of the applied field rises above a critical value in type 1, while in type 2 superconductors, raising the applied field past a critical value leads to a mixed state. So this is true. In type 1 superconductor, what will happen is so there is one critical field at C1, and above that you will not get any superconductivity, and below that you will get the superconductivity. But in type 2 superconductors, there is something called vortex states, which is a kind of mixed state. So so this statement is correct. The type 1 superconductors can tolerate impurities without affecting the superconductivity. This is true, while type 2 are more sensitive to the impurities. So this is also true. So this is true. Type 1 superconductors do not exhibit perfect Meissner effect, while type 2 do. So this statement is false. Actually, it is type 1 superconductors exhibit perfect Masnier effect. And type 2 superconductor allow some fields through them, particularly in the vortex state they allow some magnetic flux to pass through them. So the correct statement is only, so this statement is false. It is actually type 1 superconductors exhibit perfect Masnier effect, while type 2 they do not exhibit the perfect one. So it is only statement 1 and 2 are correct. Statement 3 is false. The seventh question, what it is asking, the isotope effect in tin. The following data were obtained for the dependence of the critical temperature Tc of tin on its average atomic mass capital M in the atomic mass unit. If 1 by root m is plotted on the x-axis, so the x-axis is 1 over root m, and Tc on the y-axis, the y-axis it contains Tc, which of the following curve is correct representation of the data mentioned for the tin? So we know that Tc is directly proportional to 1 by square root of m, which means that Tc is equal to some constant k times square root of m. So now what this will become? This will just become a straight line if you plot this. So, and amongst these two plots you see that only this thing represents some kind of straight line. So the answer is B only. So this is our correct answer. Let us go to the next question now. In a superconducting state, the resistivity E and V, what happens to them? In a superconducting state, what will happen is it is kind of a perfect conductor. So rho has to be 0. Rho or the resistivity vanishes. Then what we need is, so from Maxwell equation you can just write that divergence of E is equal to rho over epsilon naught, and since rho is 0, so divergence of E has to be 0. So E is usually 0. From Masnier effect we can say that Masnier effect doesn't allow any electric field, Masnier effect doesn't allow any magnetic field to pass through it. So Masnier effect tells V has to be 0 in a superconductor. And So since the divergence of E is 0 and the curl of E is also 0, so what we have is the electric field is also 0 inside the inside the superconductor, in the superconducting state. Then we go to the next question. The plot of electronic specific heat versus the temperature across the superconducting transition temperature is most appropriately represented by. So here we have to understand the fact that at T less than Tc there is a gap between the superconducting state and the normal state. So if this is a superconducting state and normal state, and there is this gap. So because of the presence of this gap, what happens? So if you want to, so what is specific heat? The specific heat means you're giving some energy to increase the temperature by a particular unit. So here what is happening? So as you fall, so with temperature, the specific heat reduces, but just after just at the transition temperature, what happens? You need to give, because of the presence of this energy delta, this energy gap delta, you need to provide some more energy now to reduce the energy by that same amount. So what happens? So you have to provide this extra energy. So that is why this sudden increase is there at the critical temperature, and then it falls. So this is a signature of that presence of that gap. So this is your correct answer. Let us come to the next question now. A superconducting ring carries a steady current in the presence of a magnetic field B normal to the plane of the ring. Identify the incorrect statement. Okay, the flux passing through the superconductor is quantized in units of Hc by E. So this is again a wrong statement. Why? Because the quantization, it tells you that it is quantized in steps of Hc by 2E, and this factor of 2 is important. The current and the magnetic field in the superconductor are time independent. So this is true. So once some current is set, it stays like that for a long time. And similarly, the magnetic field is also in the superconductor. The magnetic field is also a constant. So there would be no magnetic field because of the Meissner effect, and it stays like that for a long time. So hence it is time independent. The current density and B are related by the equation curl of J plus lambda square B is equal to constant, where lambda is equal to 0, where lambda is a constant. So this is nothing but your London's equation, similar to London's equation. So this is correct. The superconductor doesn't decay over a very long time. Yeah, since the resistance is 0, so whatever the current is set, that is actually time independent. And since it is time independent, it neither decays nor grows, it remains the same. So it is correct that the superconductor doesn't decay over time, over a very long time. So this is correct statement. To understand this, why the London's equation, so this you can refer to any book, or you can just use Ampere's law. Ampere's law says that curl of B is directly proportional to J, so 4 pi over C, and you take the curl again, so this is Ampere's law. Then you take the curl again, curl of B is equal to 4 pi over C curl of J, and this thing is gradient of divergence of B minus del square B is equal to 4 pi over C and divergence of B is always 0 from Maxwell's equation, and so from here what we are going to do is so let Vc be the velocity of the superconducting electrons, and this is going to be your equation of motion. In presence of electric field, this would be your equation of motion for the electrons, and so Bs for the subscript S stands for the superconducting electrons. Now the current density of the superconductor is minus NeVs. Now the current density, it varies as you just have to do the derivative of this, so minus Ne dVs over dt. and dvs over dt we can write it from here minus ne minus e over m, which is n e square over m into a. And now if you take the curl of e, what you get is take curl of dj over dt is equal to n e square over m curl of e. Okay, and curl of e is equal to, we know from Faraday's law for the Maxwell equations, it is minus del t of b 1 over c. And here we have del t curl of j is equal to minus ne square over mc, and it is del t of b. So what we have now is curl of j plus ne square over mc into b. This is actually a constant, but we will choose that constant to be 0. So this is your London's equation, which is there given in the question, and this has the dimension 1 over lambda square, where lambda has a dimension of length. So this is what it is. So this is nothing but the London's equation, and this statement is also true. So this is true. So the only incorrect statement is this, and that is your answer. So this is about the assignment questions in week 9. Let us go to the next review of the previous year problems. So the first question it is saying is what is the temperature dependence of the critical field of a superconductor can be described approximately by. So the correct answer is this. How does it look like? So with respect to temperature, it looks like something like this. So this point of intersection is your Tc, this is T, and this is B as a function of temperature. So at T equal to Tc it has to vanish, so it approximately looks like this. So your correct answer is actually, so it is kind of an inverted parabola. So B has to be directly proportional to minus of T square. Okay, so we need to take care of that, and then we'll have the correct answer as so BC of T is equal to BC of 0 1 minus T over Tc. So we have to make sure that the square is over T over Tc whole square, not over the entire region. Okay, so this is your correct answer is this one. Now let us go to the next question. Tin has a critical temperature and 3.7 Kelvin and the critical field 31 millitesla at 0 Kelvin. What is the tin has Kelvin, and what is the minimum radius required for a tin wire if it were to carry a 200 ampere current at 2 Kelvin? So we have to find at 2 Kelvin what is the magnetic field, and corresponding to that, so tin, you can think of it as tin wire. So it is kind of a cylinder. Okay, it has certain radius r. So the magnetic field just outside it is, so magnetic field just outside, inside there would be no, because it is superconductor. So B is equal to mu naught I over 2 pi r. So for a given amount of current, there has to be a magnetic field. So we know that this current we require is 200 ampere, mu 0 is a constant, 2 pi is a constant. This B, we have to find this at which temperature? At T is equal to 2 Kelvin. So how do we get that? T equal to 2 Kelvin is given by B at T equal to 0 Kelvin 1 minus T. T is what? 2 Kelvin over Tc. Tc is how much? 3.7 Kelvin whole square. So from here you will get B. So T at 0 Kelvin, how much it is? 31 millitesla. So it is 31 millitesla into 1 minus 2 over 3.7 and whole square of this. So this is how you will get B. After obtaining B here, you have to put it back here. So R will be mu 0 I over 2 pi B. So this B you have to plug in here, and after plugging in there, you know all the other values. So what you get is, so let us just, R is equal to mu naught is 4 pi into 10 to the power minus 7 divided by 2 pi divided by 2 pi into I is 200 and B is this 31 millitesla into 10 to the power minus 3 1 minus 2 over 3.7 whole square. So we have to calculate, so this would be the, so this is radius. So if you calculate this, the radius turns out to be .8 mm. Now let us go to the next question. Consider the expression for the binding energy of Cooper pairs. So the expression for binding energy of the Cooper pair is already given here. So it is 2h bar omega d over 1 minus exponential of 2 over lambda, where lambda is some constant. And we have to find this expression for lambda less than 1. So what it means is it is less than 2 also. Okay, so and that means lambda over 2, sorry, what this means is 1 is much greater than 2 by lambda. 1 is much smaller than 2 over lambda. That means e to the power 1 is much smaller than e to the power 2 by lambda. And e is what? This is 2.7, so it is anyway greater than 1. So 1 is really very small than 2 over lambda. Okay, so what happens is this 1 is so small that we can simply neglect h bar omega d 1 minus a very big number. So we can just write, we can ignore 1 and 2 over lambda. Note that there is this minus sign which is really crucial. So what you have is minus 2 h bar omega d e to the power minus, so exponential of minus 2 over lambda. So your correct answer will have a minus 2 omega d, and so this is your correct answer. Let us go to the next question now. Choose the correct statement regarding BCS wave function. The BCS wave function is an eigenstate of, so let us first see what is the BCS wave function. Okay, so choose the correct statement regarding the BCS wave function. The BCS wave function, it is given by it is the product over all the Cooper pairs, and this Cooper pairs where this there are two states of this Cooper pair. One state is 0 and the other state 1. 0 means that the Cooper pair with momentum k plus k and minus k have not been generated, and 1 sub k, it means that the Cooper pair with momentum plus k and minus k, they have been generated. So we have to take the product of all such Cooper pairs, like all possible Cooper pairs, and this k, it runs from so the number of values of this k is of the order of 10 to the power 23, or the Avogadro's number. So this is a multi-particle wave function, and as you can see, this is, and this uk square plus vk square, this has to be 1. So this constant is there, like this is the constant of normalization. Okay, so what we have now is the BCS wave function is an eigenstate of the number operator. This is false because it is so from here it is clear that it is not the eigenstate of the number operator. The number of pairs can be fixed by integrating the phase. So that is true because this is an eigenstate of the phase. So the number of pairs can be fixed by integrating over the phase. So this is correct. The BCS wave function is not an eigenstate of the phase. This is false because it is an eigenstate of the phase. The BCS wave function is, so here what it is saying, it is sum over k, uk 0 sub k and vk 0 sub k. So this statement is false. It is actually the product of all such possible Cooper pairs. So the only correct answer is this one. Now consider the expression. So this is again the London's equation. So under the steady state, which of the following condition is required to write this equation? So what is steady state? The steady state means that the current is flowing in a steady way. So there is no extra charge generated. The J is basically this Js in a steady flow, the current density in a steady state, it is given by divergence of Js is equal to 0. What it means is so neither any superconducting electrons are getting generated nor they are annihilated. They are simply flowing. So this is the condition for the steady state. Now what we need is we have to use this condition in the above expression and determine what is the required condition. So to do that, let us start with the given equation, given expression. Curl of Js is equal to minus C over 4 pi lambda L square into B. What we are going to do now, we have to use this B is equal to curl of the vector potential, and minus C over 4 pi lambda L square curl of the vector potential. So now what we have under this curl is, we can rearrange and write it as like this: C over 4 pi lambda L square is equal to 0. So now we can choose this has to be 0 or this has to be some constant. Let the constant. Now we take the divergence of this expression. So what we have is divergence of Js plus the constant 4 pi lambda L square divergence of A is equal to divergence of a constant is always 0. So at a steady state, now we put the steady state condition. The steady state condition is divergence of S is 0, Js is 0. So this is your steady state condition. If we employ that here, so 0 is equal to C over 4. So 0 plus 4 pi lambda L square divergence of A is equal to 0. So what we have is this divergence of A, this has to be 0 because the C, 4 pi lambda L, these are non-zero quantities. So from here what we have is divergence of A, this needs to be 0. Now what is so this condition is also called the Coulomb gauge. So to write that equation, this condition, we have to work in this Coulomb gauge, which basically means that the divergence of A is 0. Let us go to the next question now. Which of the following is false regarding the BCS gap? So the expression for the BCS gap, it is given by false. So the first one, this is actually the expression for the BCS gap. So sine hyperbolic x is e to the power x minus e to the power minus x over 2. So when x is really small, sorry, when x is really large, if x is really large, sine hyperbolic x, it can be represented as e to the power x by 2. Okay. Why? Because this e to the power minus x becomes negligibly small. So if you use so usually what happens is this v naught z e f, this is very small. So delta becomes so we have to use this e to the power, so exponential 1 over v naught z e f naught by 2, which is equal to 2h bar omega d e to the power minus 1 by v naught z e f naught. So this is your correct expression. Okay, one of the correct expression. So starting from here we showed that this is true, and there is this no minus sign here, so this is false. The fourth option, it says that the perturbation calculation cannot provide the correct expression for BCS gap. So this is true. You cannot obtain the BCS gap from a perturbation calculation. So you get this by solving for the so you first take the BCS wave function, and from there you calculate the average energy, and from there you get that BCS wave function, and you have to consider that coupling of phonon and the electrons to get the Cooper pairs. So the formalism is not a perturbation calculation. So that is the important point here. Which of the following statement is valid for phonons? So phonons are nothing but, what are phonons? Phonons are quantum of lattice vibrations. And they are actually bosons, and that is why they satisfy or they obey the Bose-Einstein statistics. So they have spin half. So this statement is clearly wrong, because if it has a spin half, then it would mean that it is a fermions, which is not true. The phonons obey Bose-Einstein statistics. This is true because phonons are bosons and hence they obey the Bose-Einstein statistics. They have the momentum h nu over c. So this is, if you see, this is a statement of the dispersion relation. Okay. So momentum means P is equal to h nu over c. So P is, you can write as h bar into k. K is the momentum or the wave vector, and this you can write h by 2 pi into 2 pi nu over c. So h by 2 pi is h bar and 2 pi nu is omega by c. So what you have is omega equal to c k. So this is your dispersion relation. Okay. But for phonons, the dispersion relation, it looks like this: k and omega k, and if it is a single lattice, then it is something like this, and it bends over here. And and in some cases there would be this optical band. So, but the point to note here is that this, if you see for the phonons and compare that with light, for light it is like really very steep, this slope, omega equal to ck. Case. So this is really very steep as compared to this. So this mode is called acoustic mode, and so they two never intersect each other, and this looks so this is an exaggeration that you can see even this angle. So it is so steep that it is almost coinciding with this y-axis line. So this dispersion relation is that of the light, and that is why this statement that these have the momentum this is wrong. So this is wrong. Represent vibration of individual atoms in a solid. So this statement is true because so it is not of the individual atoms, it is the collective motion of the. So a phonon represent the way this lattice atoms, the atoms in this lattice, they move collectively. Okay, so it is not a representation of vibration of the individual, rather it is that of the collective motion of all atoms. Okay, so each of the state, for example, like there would be a state here moving like this. So it is that collective motion which is described by the phonons, not the individual atoms. So that is why this is also wrong. Okay, now the next question: which of the following is false about the BCS superconductors? The superconducting property can be destroyed by the application of magnetic and electric fields. So this is true because at a given critical temperature, let's say you fix the critical temperature. Now you increase the field, so increase the magnetic field, let's say, if you increase the magnetic fields at a particular temperature, so there would be a critical field beyond which the superconducting property will not be there. So the superconducting property is destroyed by the strong electric and magnetic fields. So this statement is true. The transition temperature varies as the atom is substituted by its isotope. So we have seen that the transition temperature or the critical temperature Tc is inversely proportional to the square root of the mass. So this statement is true that the transition temperature varies as the atom is substituted by its isotope. So this statement is true. The variations of the critical temperature for BCS superconductor is given by, so here what it is saying that Tc inversely proportional to 1 over m, which is false. The correct one is it has to be falling as 1 over root m. This square root is important, so this statement is wrong. The elastic properties, or this is false, which means that this is your answer. So this is your answer. The elastic properties, crystal structure and thermal expansion remain constant as system becomes superconductor. So this is true. Only the electronic properties will change, electronic transport properties will change. So this is true. The other properties, they are intact. Now we go to the next question. In a magnetic material, the field strength. So what is field strength? Field strength means this magnetic field strength H. It is given 10 to the power 6 ampere per meter. If the magnetic susceptibility of the material, magnetic susceptibility is this, is 0.5 into 10 to the power minus 5. The intensity of magnetization and the magnetic field B in the material are how much? So let us first calculate. So this is just the basic electrodynamics formula. B is equal to mu naught m plus h, and you have to use m is equal to chi h, and if you just substitute here, you know h from these two. So let us first calculate m. M is equal to chi times h, which means 0.5 into 10 to the power minus 5 into 10 to the power 6 ampere per meter. So it is 0.5 into 10 ampere per meter, which means 5 ampere per meter. This is your magnetization. So either the answer is this or this. So we have to calculate B to see which one is the correct answer. So let us just do that. We know M and we know H. So B will be is equal to mu naught is 4 pi into 10 to the power minus 7 Tesla. So if you keep everything in SI unit, it will become Tesla. M is 5 and H is 10 to the power 6. This much Tesla. So now you see this 5 is really very small as compared to 10 to the power 6. So, or what you can do is 4 pi into 10 to the power minus 7 plus 6, 1 plus 5 into 10 to the power minus 6. Okay. So what it amounts, so let us calculate 4 pi. So it is 4 into 3.141 into 10 to the power minus 1 into 1 plus, it is 0.12345 So this is so small that we can simply neglect this. So what we have is, this is 12.5654 into 10 to the power minus 1 Tesla, which is 1.2564 Tesla. So, or it is approximated as 1.257 Tesla. So this is your correct answer, the first one. Now let us go to the next question. In a superconducting wire, a long conducting wire produces a magnetic field of this value on its surface due to current through it at temperature T. So you have been given a very long it produces a magnetic field of, so the magnetic field would be, if the current flows in this direction, the magnetic field would be so the magnetic field would be like this in circular. So it is V is equal to 200 into 10 to the power 3 ampere per meter on its surface due to a current through it. So the current through it, so this is at temperature T is equal to 5.4 Kelvin. Its critical magnetic field, so Vc0 at temperature T equal to 0 is 250 into 10 to the power 3 ampere per meter. Find the critical temperature Tc. So we have to find the critical temperature Tc. Okay, so we have to use the formula V at T is equal to 0, T equal to some temperature. It is given by V at T equal to 0, 1 minus T over Tc whole square. Okay, and we have to find this critical temperature, but for this particular magnetic field, so this magnetic field is already given. That magnetic field at temperature 5.4 Kelvin is 200 into 10 to the power 3 ampere per meter is equal to B at T equal to 0 is 250 into 10 to the power 3 ampere per meter into 1 minus T is the temperature is 5.4 Kelvin over Tc whole square, and you have to do this. So the only unknown variable is Tc. You just have to calculate. So let us just calculate. This cancels this. So it is 4 by 5 is equal to 1 minus 5.4 over Tc whole square. This implies 5.4 over Tc whole square is equal to 1 minus 4 by 5 equal to 1 by 5. This implies that Tc is equal to 5.4 into root 5 Kelvin. So this will give us 5.4 into root 5. That is around 12.5 0.07 Kelvin. So this is how you calculate the critical temperature. So this is your critical temperature. So these are all the questions we had for today's discussion. If you have any question or doubt, you can ask me. You are able to understand how to solve the problems, right?